Welcome. We are diving deep into the measure phase of DMAIC. This is the part where we stop guessing and start knowing. It's where all those assumptions from the define phase get put to the test against cold, hard facts.
So, here's our game plan. First, we'll talk about why this phase is the foundation for everything. Then we'll get practical with data collection plans. After that, we'll dig into making sure you can actually trust your numbers with MSA and then calculate your process capability. And of course, we'll wrap up with some real-world tips and tricks to make sure you get it right.
All right, so we've already defined our problem. But right now, it's mostly based on what we think is going on. The measure phase is all about finding out what's actually happening. We're establishing a factual baseline, a starting point that's going to anchor our entire project.
Now, measure is the second step in the DMAIC framework, and let me tell you, trying to rush through it is a classic mistake. A solid measure phase completely sets you up for success, but a weak one, well, that almost guarantees you'll waste time solving the wrong problem.
The point here isn't just to go out and grab a bunch of random numbers. No, we are on a mission. We need to collect accurate data, we have to validate our measurement systems, and then we use all that good info to paint a really clear statistical picture of our process just as it is today.
So, how do we actually do this? Well, you can't just run out onto the floor with a clipboard and hope for the best. Success here starts with a detailed roadmap, and that's what we call a data collection plan, or a DCP for short.
This old saying is basically the unofficial motto of the measure phase. Think about it. If you collect flawed, biased, or just plain irrelevant data, your analysis is going to be flawed, your solutions will totally miss the mark, and honestly, the whole project could be a waste of time. Your DCP is your insurance policy against that happening.
What's so great about this framework is just how thorough it forces you to be. You have to figure out what you're measuring, your key metric or Y, and all the potential causes, your X's. But listen, pay super close attention to the operational definition line. This is absolutely critical. Everyone, and I mean everyone on the team, needs to agree on exactly what a defect means or how cycle time is measured, right down to the last detail. It prevents so much confusion later on.
Okay, so we have a solid plan to collect data, but before we take a single measurement, we have to ask a really tough question. What if our ruler is broken? Seriously, what if the variation we think we're seeing in the process is actually just coming from our own measurement tools and methods?
And that is exactly where measurement system analysis, or MSA, comes into play. Its whole job is to figure out how much variation is coming from your measurement system itself. That way, you can be totally confident that the data you collect reflects the true performance of your process, not the noise from your tools.
Now, you'll typically use one of two main types of MSA. If you're measuring continuous data, things like length, weight, or time, you're going to use a gauge R&R study. But if your data is discrete, like a simple pass-fail inspection, you'll use an attribute agreement analysis. That's perfect for checking if different inspectors are all making the same judgment calls.
When you get the results from your gauge R&R, these are the two numbers that really matter. First, look at the percent contribution. You want the variation from your measurement system to be less than 10%. Second, your system has to be sharp enough to actually tell the difference between parts. That's measured by the NDC, or number of distinct categories, and the goal there is a score of 5 or more.
And this brings us to the golden rule of MSA, and it's non-negotiable. If your study fails, you stop. You do not pass go, you do not collect data. You have to fix the measurement system first, whether that means getting new equipment, doing more training, or just writing clearer procedures. Collecting data with a broken ruler is just completely pointless.
Okay, so we have a plan, and we've proven our measurement system is trustworthy. Now, finally, we can use our data to answer the million-dollar question, how capable is our process of actually meeting our customers' requirements?
This bell curve, this is the classic picture of process capability. See those wide lines on the sides? Those are your customer's specification limits. Think of them like the goalposts. The curve in the middle is your process. The name of the game is to have a narrow, consistent process that's centered smack dab in the middle of those goalposts. So to measure this, we use two key metrics, CP and CPK. Now think of it like this. CP tells you if your car is small enough to fit in the garage, but CPK tells you if you've actually parked the car between the lines. CPK is the true measure of how you're doing right now because it looks at both the spread and how well you're centered.
And this table here is basically your scorecard. If your CPK is less than 1, your process is just not capable of meeting customer specs. It's a failing grade.
Many industries will tell you that a CPK of at least 1.33 is the minimum acceptable level. And if you hit a CPK of 2.0, well, that is truly world-class Six Sigma performance.
Okay, now that we've covered the core tools, let's talk about how to really pull this off successfully in the real world, and more importantly, how to avoid the common traps that can completely derail a project.
Seriously, these are your keys to success. Doing a small pilot run of your data plan can save you weeks of agony later. Stratifying your data, breaking it down by shift or by machine or by operator, that's often where the biggest aha moments are hiding. And please, never, ever forget to document your baseline CPK right in your project charter. That number is your official starting line for the whole race.
So let's wrap this all up. A well-executed measure phase is truly transformative. It moves the entire conversation away from opinions and "I think" to a shared understanding that's based on objective, validated data. It really is the rock-solid foundation for all the analysis that's about to come. And how do you know when you're done? You know you successfully completed the measure phase when you can confidently check these 3 boxes. You have enough good data, you 100% trust your measurement system, and you know exactly how your process is performing today.
And that, right there, is the exciting question that launches us directly into the analyze phase. With our validated data finally in hand, we are ready to start digging in, looking for patterns, and hunting for the true root causes of our problem.